All right, so we're checking out class 61 now. I'm going to skip the first page. The first page has some videos and a simulation. You could check those out if you want. Those of you who are in class should have answered all of these things. So if you have questions about that, you can ask me. But I'm going to skip this page for now and go on to the second page. So on the second page, we start with the law of conservation of energy. Which states that in a closed, isolated system, energy can neither be created nor destroyed. Rather, energy is conserved. Just a reminder that a closed, isolated system is a system in which there is no net external force. So our energy equation is the total energy of a system is equal to its potential energy plus its kinetic plus its internal energy. Now that equation can be found on your equation sheet. The one equation that is not on your equation sheet, though, is the conservation of energy formula, though the conservation of momentum formula is on your equation sheet. Frequently, when we do these problems, I'm going to expand this, and I'm going to say that the total energy of the system is equal to the potential energy initial, just fix that I a little bit, plus the kinetic energy initial, plus the initial internal energy of the system, which in this class will always be 0, is equal to the final potential energy of the system plus the final kinetic energy of the system plus the final thermal energy of the system. You notice this image over here shows that the kinetic energy plus the potential energy will always equal the total energy. Though the potential energy may decrease, the kinetic energy must increase in turn. This diagram doesn't include Q, but you could also include Q as another bar in this diagram. So let's look at a question here. It says, after a 65 Newton weight has fallen freely from rest, a vertical distance of 5.3 meters, the kinetic energy of the weight is... So let's start with our conservation of energy equation. I'm just going to copy it and bring it down here. Potential energy initial plus kinetic energy initial plus Q initial equals potential energy final plus kinetic energy final plus Q final. Now, there's no mention of any sort of friction in the system, so we can assume that all the Q values are 0. There's no internal energy, there's no friction, nothing like that. So let's draw a small picture of what's going on here. So we have an object that's falling. Its initial position is up here. We'll call this initial. And it falls, and its final position is down here, the instant before it hits the floor. All right, so at this position, we definitely have some potential energy, but we have to realize that here we have no kinetic energy because the ball is at rest before it falls. Okay, so our initial kinetic energy of the system is 0. We can just go ahead and cross that out. Now when the ball falls and reaches the bottom, since it has 0 height, it also has 0 potential energy at its final position. Therefore, potential energy final is also 0. Therefore, we just plug in. We have potential energy. Our equation is mgh, using the initial height, is equal to kinetic energy final, which is 1/2 mv squared. Okay? Actually, this question actually just asks for the kinetic energy final, so we don't even need to write 1/2 mv squared. We can simply write Ke final. So now to solve for KE final, we have to find MGH. Now, just be careful. 65 newtons, this given up here, is actually our value for mg. So we can just plug that right into mg. You don't need to multiply by 9.8. We also need the height, which is 5.3 meters. So if we multiply those two together, we have 65 times 5.3, and we get a value of 344 joules. 0.5. Looking at practice question number 4 here, it says that an object thrown straight upward, or an object is thrown straight upward. Which graph best represents the relationship between the object's kinetic energy and the height of the object above its release point? So one thing to realize is that when a ball is thrown straight up into the air, it's slowing down as it goes up. So if it's slowing down as it goes up, its velocity must also be going down. If its velocity or speed is going down, it has less and less kinetic energy as it goes up. So it can't be this choice here. It can't be this choice here because the kinetic energy is constant. It can't be the choice here because the kinetic energy here is increasing. So the only choice left is this one right here, where the kinetic energy goes down as it gets higher. So number 5 is a multiple choice question from years past. It does take a bit of work. I'll go through the long way to do it. But as you practice these more and more, you'll definitely get better at doing this quicker and quicker. So we have a 1.8 Newton ball and it's dropped from a height of 10 meters and it falls through the air to the ground. The kinetic energy of the ball is 11 joules the instant before the ball strikes the ground. The maximum amount of mechanical energy converted to internal energy during the fall is, so we know there's Q in here, so we can't just ignore that this time. So let's start with our conservation of energy formula. Potential energy initial plus kinetic energy initial plus Q initial equals potential energy final plus kinetic energy final plus Q final. In this class, Q initial will always be 0, so we'll get rid of that. So the ball definitely has potential energy because it has a certain height it starts from. So that would be mgh. I'm just going to abbreviate that a little bit though. And mg, I know, is equal to 1.8 newtons. H, initial, is 10 meters. And my final kinetic energy is 11 joules. So my initial potential energy is mgh. So, sorry, because that's got to be mg there. That 1.8 newtons is mg, not just m. So my mg is going to be 1.8 newtons times my initial height of 10 meters. My initial kinetic energy is 0 because we can assume the ball starts at rest when it's dropped. And that's equal to, the final potential energy is also 0 because it's at ground level. The final kinetic energy is given to us, that's 11 joules. And Q final is our unknown. So this comes out to be 18 joules equals 11 joules plus Q final. Therefore, Q final must be 7 joules. If we look at number 6, it says, your friend makes a claim that energy is not always conserved. She drops a ball from her shoulder height. It hits the floor and stops. Explain why energy is conserved in this case. So all of the energy must have been turned into like internal energy or thermal energy or something when it stopped on the floor. So what does that look like? So it could have vibrated the floor. That takes energy. It also could have converted to sound energy. It could have turned into heat energy through friction in the air. And another one that a lot of people don't think of is some of that energy could have gone to deforming the ball. Like if a tennis ball falls and hits the ground, it does flex a little bit. So these questions on the back are some practice questions using conservation of energy. Now, the first question, number 7 here, I want you to do both ways, once using energy and once using kinematics. So I'll start with using kinematics because that's what we learned first and we did pretty well with earlier in the year. So if a cannon is shot vertically upward with a velocity of 210 meters per second, how high does the ball go? So for this one, our initial velocity is 210 meters per second. Our final velocity at the apex is 0 meters per second. Our acceleration is negative 9.8 meters per second squared, and our distances are unknown. So here we could use the equation Vf squared equals Vi squared plus 2AD. Vs squared would be 0, the initial squared would be 210 squared plus 2, negative 9.8 d. Throwing these into our calculator, let's see what we get. So 210 squared is equal to 44,100 minus 19.6 d. Solving for d, we get a distance or a height of 2,250 meters. Now let's see if we can do this with conservation of energy. So I put this little box here to draw a picture, though you don't necessarily need to draw a picture. I'll just do it. So if we start at ground level, here's our initial position, where our initial potential energy is equal to 0, but we do have kinetic energy because we have a velocity initially equal to 210 meters per second. The ball goes up. Up here, we do have potential energy. We're not really sure what that is yet, though. And we have a velocity here of 0 because we're at our apex. So to find the height, we can use our conservation of energy equation. Now we're going to leave Q out of this because there's no mention of friction, no mention of internal energy or anything like that. So we have potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Now if we just plug everything in, all of our equations, we have mgh initial plus 1/2 m v initial squared equals mg h final plus 1/2 m v final squared. So you'll notice here a really important idea with conservation of energy is frequently you can cancel out all of the masses. You'll notice we have mass in every term here, so they all cancel out. Now plugging in what we know, at our initial position, I'm going to leave the units out. Our g value is 9.8, our height is 0. We already said that term would be 0. Plus 1/2 210 squared equals 9.8 times h final. The final height, that's actually what we're looking for. Plus 1/2 v final squared, and we said our final velocity would be 0. So this term goes away, and this term goes away. If you solve for h final, you'll end up getting our final height is equal to 2,250 meters, just like it was using kinematics. Now, this is actually the reverse problem. Now we're dropping a ball, and it has a final velocity of 15 meters per second when it reaches the bottom. So the ball's initial position is here, and its final position is down here. So it's important to note that our initial kinetic energy is 0, and our final potential energy is 0. And there's no mention of friction or heat or internal energy here, so there's no Q values we need to worry about. So just to skip a little bit here, I'm just going to skip right to the line that our potential energy initial is equal to our kinetic energy final. So we have mg h initial, which is our unknown, we're looking for that initial height, equals 1/2 mv final squared. Notice here that masses cancel out again. We're not given mass, so we couldn't use it if we wanted to. So we have g is 9.8, h initial is our unknown, equals 1/2 of 15 squared. So we have 99.8 times our initial height equals 15 squared is 225, and half of 225 is going to be 112.5. Divide both sides by 9.8, and we get about 11.5 meters. So just some practice multiple choice questions. Where's the pendulum's kinetic energy to maximum? So what you see here is the pendulum swings from A to B to C. At points A and C, it has more height, so it has more potential energy. When it swings, all of that potential energy turns into kinetic at the bottom, B. So we're going to have the most kinetic energy at B and the most potential at A and C. And as time goes on, the total mechanical energy of the system remains the same. It goes from kinetic to potential and back. Now, number 12 at the end, you didn't have to do. That was a bit of a challenge question. If you want to see how to do that one, feel free to ask me, and we go over how to do it.